Dear friends, colleagues, for me it's a great pleasure to be here. First of all, I would like to thank organizers to invite me to take part in this conference. I would like to thank also to Ukrainian army for defense against Russian aggression, and in fact for the opportunity to be here. I would like to thank also to all people and all countries that support Ukraine, support us in this war. So thank you very much. Glory to Ukraine and Slava Ukraine. So, and now let us concentrate on my talk. So, subject of my talk is study of spin system of quantum computer. This result which I present here is done in collaboration with Professor Christina Agnatenko and from our department, and also in collaboration with Hanna Laba from Lviv Polytechnic University. So plan of talk is here, introduction, very short introduction. Then I plan to describe how to detect energy level of spin system on quantum computer. I present two methods for this paper, two methods for this goal. And then I would like to show application of this method to observation of spin tunneling on quantum computer. It is a very interesting phenomena such as tunneling of spin, which can be observed experimentally, and therefore it is interesting to observe also this phenomena on quantum computer. And finally, conclusions. Okay, so let us begin. So maybe first scientist who mentioned it about quantum computer, quantum device was Richard Feynman. And here is a publication where section 4 is titled Quantum Computers, Universal Quantum Simulators. So very long time ago, Feynman proposed to use quantum computers as a good device for simulation quantum phenomenon. Why we consider just spin system and spin 1/2 system? It is very simple to explain, because you can find that a quantum bit, it is a two-dimensional quantum system, and also spin 1/2 is also two-dimensional quantum system. Therefore, we have mapping of bit on spin 1/2 or spin 1/2 on quantum bit. So in fact, it's the same. Therefore, spin system, or maybe in general arbitrary binary quantum system with binary degree of freedom, are the most suitable for simulating this system with quantum computer, quantum device. Okay, and now let us consider just some quantum system. And there is question how we can find energy spectrum, energy levels using quantum computers. The idea is to study evolution of wave function, evolution of some mean value, and maybe we can study evolution of mean value, can get from this time dependence to get energy levels. Of course, yes, because we can easy to calculate evolution, to write evolution in this form. Here I use as basis vectors eigenvalue of Hamiltonian E. Here it is eigenvalue of Hamiltonian H, and then time dependence or time evolution of wave function can be written in this form. Here is written initial state, And using this evolution, you can easily calculate arbitrary mean value of some operator A here. And important that the result can be written as here in this form. So you find that here we have a transition between energy levels. So we have harmonic oscillations with frequencies, and frequencies depend. It is just exactly transition frequency of transition between energy levels, different energy levels of system. So in such a way, we can find study time evolution of some operator. You can find the time dependence is periodic, not periodic, but contains harmonic function with frequencies which is transition between energy levels of system. So now let us consider Fourier transform of this time dependence. You can easily find that this Fourier transformation have delta peaks exactly at points of this transition frequencies. The whole idea is the following. We can study, using quantum computers, time dependence of some operator, some physical value. Then we consider Fourier transformation, and peaks of this Fourier transformation give exactly frequency of transition between different energy levels. Okay, so in such a way, on the quantum computer, we study time dependence of some physical value. Then, using classical computer, we calculate Fourier transformation, and from this Fourier transformation, we get a transition between energy levels. Of course, using quantum computer, you cannot have exactly Fourier transformation, continuous Fourier transformation. In fact, we have some discrete time when we measure mean value. And here I rewrite, show you here Fourier transformation can be considered as discrete Fourier transformation. But nevertheless, this Fourier transformation also have peaks at points of this frequency of transition between different energy levels. Okay, now let us consider the next problem. So in such a way, as I show here, we can find from Fourier transformation, you can find transition between energy levels. But what about energy levels? How to find not transition between energy levels, but exactly energy levels? And here idea is the following. Let us consider some operator A which anticommutes with Hamiltonian. So suppose we have operator A which anticommutes with Hamiltonian, and then you can easily find also properties of energy spectrum. So in this case, you can easily find that energy spectrum is symmetric with respect to inversion energy. So when you can find operator which anticommutes with Hamiltonian, then energy spectrum is symmetric with respect to inversion. And what is interesting that in this case, these properties of energy spectrum is related with supersymmetry algebra, or with supersymmetry of the system. Really, this operator A can be treated as a Witten parity operator. You can construct two supercharges, and algebra of these supercharges is written here. It is exactly algebra of supersymmetry for two supercharges, and this algebra are responsible for symmetric properties of energy spectrum. Okay, so in this case, when operator anticommutes with Hamiltonian, we have very important properties of mean value, time dependence of mean value. Really, you can easily find that when operator anticommutes with Hamiltonian, you have these properties. You can exchange exponent and operator, and then here you have pluses and minus. So then for mean value of this operator, you have such dependence on time. And you can find that here you have double energy levels of system, or double frequency corresponding to levels J. So here we have no transition between different energy levels, but exactly energy levels when we study mean value of operator which anticommutes with Hamiltonian. It's very important because in such a way we can find not transition but exactly energy levels of system. So main idea here is to use for calculation time dependence of some physical quantity is to use such physical quantity operator of which anticommutes with Hamiltonian. So then I write here once more this dependence. And what about Fourier transformation? Fourier transformation is here. Is here, and you can find that now we have peaks at points which corresponds to double energy levels or double frequency corresponding to energy levels. Sorry, here must be J. So omega J, it is energy divided by Planck's constant. So then idea is the following. We study on quantum computer type dependence. We find type dependence of this operator. And then using classical computer, we calculate Fourier transformation. We have peaks. And these peaks indicate energy levels of quantum system. Of course, first of all, we consider one of the simplest system. It is spinning magnetic field. Hamiltonian is written here. Magnetic field is directed along z-axis. Here you can easily find operator which anticommutes with this Hamiltonian. Here such operator can be x sigma x Pauli matrix, x component of Pauli matrices, or it can be also sigma y, but here we consider just exactly sigma x. And here is a simple protocol for calculation time dependence of this operator. Here we create, I forget to stress that in this case also is important initial state of quantum state system. So this operator create initial, it is Hadamard operator, and this operator create initial state, which is superposition of basis vector of quantum computers 0 and 1, or spin up and spin down. 0 corresponds to spin up, and state 1 corresponds to spin down. So this operator create initial state. This operator Rz, it is a rotation operator, corresponds exactly to evolution operator of system with Hamiltonian age. On quantum computer, we can easily create, not always easy, but in this case really easy, create evolution operator for spin in magnetic field. It is a rotation operator along that axis, and this angle phi is related with time. Here you can find this relation. Phi, of course, it is omega 0 multiplied by time t. It is angle phi. Here it is operator which we use it in order to calculate just exactly sigma x, not sigma z, because using quantum computer you can measure some quantity in basis 0 and 1. But here we must calculate not z component, but sigma x. And here is explained how to calculate sigma x. It's very easy. We transform this mean value of sigma x. This operator, it is evolution operator. This operator plus it is created by Hadamard operator, and mean value of sigma x is here. And then we can rewrite this mean value in this form, where it is some new psi tilde, some new wave function or some new state vector of this system. Important that we can transform sigma x into sigma z, and then we can easily calculate this mean value on quantum computer. Okay, so what we get here, I write this, show you the structure of IBM's quantum computer. It's IBM Quantum Computer Manila, and here is result for calculation of this mean value of sigma x on quantum computer, and as well here I show you continuous line. It is theoretical result. You can find good fitting of theoretical result and experimental result. This crosses which we get using quantum computer. Not bad. It's good relation between theoretical and experimental result. Experimental, I mean calculation of quantum computer. Okay, so here result for Fourier transformation. It's not exactly delta peak, but it is you can find good peaks which corresponds to energy level of system. Here is just exactly double energy levels of spin in magnetic field, and you can find very nice result which corresponds exactly to theoretical result of energy levels. So, but it is very simple system. It is spin in magnetic field, but even here I would like to stress that using quantum computer for study spin system in magnetic field, it is enough to have quantum computer with one bit, with one quantum bit. Of course, in classical case, it is impossible to find any result using only one classical bit. But for quantum computer, one quantum bit is sufficient to have one quantum bit in order to get evolution of spin in the magnetic field and find energy levels of this system. Of course, you find also that this spectrum is symmetric with respect to inversion of energy, plus 2 and minus 2 double energy levels of system. And it is just exactly related to the supersymmetric properties of this system, because here we can easily find operator which anticommutes with Hamiltonian. So important point of this method here, it is just to find operator which anticommutes with Hamiltonian. Okay. Now, what about more complicated system? Let us consider spin chain. Spin chain which contains 3 spins, 0, 1, and 2. It is Ising model with ZZ interaction. In fact, very simple model, but let us look what about calculation of energy spectrum using quantum computers for such a model. Of course, it is more complicated than spin in magnetic field. Here we have 3 spins. In this case, we can also easily find operator which anticommutes with Hamiltonian. Sigma 1x anticommutes with this Hamiltonian. Really, because sigma 1x anticommutes with sigma 1z, and sigma 1x commutes here in second term in sigma 1x, and commutes with 0 and second spin. So, of course, this operator anticommutes with this Hamiltonian. So now we can use the same method for calculation energy level. Here we create initial state with this superposition of all possible states of 3 spins. This Hadamard operator creates superposition of all possible states of 3 spins. Then these 3 operators corresponds to interaction of 0, 1, ZZ interaction. You can easily find that evolution operator with such term exactly corresponds to this 3 operator. The second term in Hamiltonian corresponds evolution operator with this second term of Hamiltonian corresponds to this 3 operator. And here we measure this operator is used for measure x component of fast spin. It's just exactly fast spin. 0 spin, fast spin, and second spin. We have 3 spins. So time evolution we can which we get using quantum computer is here. You can find also not bad result, but not so good as in the case of 1 spin in magnetic field. You can find here not so good result, but nevertheless, let us consider Fourier transformation, Fourier transform of this discrete Fourier transform, because this process corresponds to a result which we get on quantum computer. But discrete Fourier we use, of course, here discrete Fourier transformation, and what we get for a result. Once more, we get very good result. We have 3 energy levels corresponding to our system, which exactly corresponds to theoretical result. 0 energy levels, and here plus minus 4. And once more, this spectrum is symmetric with respect to inversion of energy. And once more, I would like to stress that this property of spectrum is related with supersymmetric properties of our system. Here exists operator which anticommute with Hamiltonian, and as a result of this anticommuting, such Hamiltonian have symmetric properties of energy spectrum with respect to inversion of energy. Okay. Now consider more complicated system. It is Ising model on square. So let me omit explanation, details of explanation. I only stress that for this case, it is Hamiltonian on a square, and you can easily find that operator A, which anticommutes with Hamiltonian, is sigma 0, sigma 2 xx. You can calculate and find that sigma 1 or sigma 2, second Hamiltonian, anticommutes with operator A, with this operator. So in these 2 cases, I consider here two different Hamiltonians with the same interaction, and here we have opposite interaction with minus. So 2 different Hamiltonians, but 2 Hamiltonians on the squares, Ising model, but with different coupling constant. And in the first and the second case, operator which anticommutes with Hamiltonian is here. You can find such Hamiltonian which anticommutes with, you can find such operator A, which anticommutes with Hamiltonians. Okay, so in order to get energy spectrum, we must to find time evolution of mean value of this operator, and then using Fourier transformation, we find peaks at points which corresponds to energy levels of system. So here is quantum algorithm for calculation. Let me omit details. It's very similar to the first case, but more complicated. And here we must to measure mean value of product of two operators. And as a result, we must measure zero spin, and we must measure second spin corresponding to this mean value. As a result, what we get this result for mean value of this operator is this for first Hamiltonian and for the second Hamiltonian. It is strange, but it is we have some shifting of theoretical result and experimental result of quantum calculation, shifting on some constant. You can find here it shifted down all these crosses. But for the second Hamiltonian, the result is more good, more better. Okay, let us look at Fourier transformation. Fourier transformation also gives a very nice peak at the point which corresponds to energy levels. Okay, I will omit details of many details concerning energy spectrum. Only say that we have here also symmetric properties of energy spectrum with respect to inversion, and it is result of supersymmetric properties of this system. Because here we can find also operator which anticommutes with Hamiltonian. Okay, what about more complicated system? Let us look 6 spins. This one, 1, 0, 1, 2, and these 3 spins here. So we consider spins on square lattice, 6 spins. Hamiltonian is written here. It's more complicated. And what is interesting, in this case, we can also find operators which anticommutes with this Hamiltonian. It is product of 3 spins, spin 0, this one, and this one spin, and product of these 3 spins, x component of these 3 spins, anticommutes with this Hamiltonian. So we have the similar situation as in previous case. Now we consider evolution of this time operator. Protocol quantum algorithm for this case is more complicated, but we can calculate using this quantum protocol mean value and time dependence of mean value of these 3 spins. And what is result? Result is here. It's very bad result. Look here, this continuous line it corresponds to theoretical result. You can easily calculate evolution using calculation, theoretical calculation. And here, these crosses, blue crosses, corresponds to results which we get using quantum computer. When we look for the first time at this result, it was impression that it is very bad result, and Fourier transformation we will not get good Fourier transformation. We will not get peaks. But okay, let us look what result is for Fourier transformation. Look here, it's not so bad. It's not so bad. Here I presented you a result for Fourier transformation, and here we use quantum simulator. It is impossible to consider in this case not so many spins, only 6. So quantum simulator gives a good result. Peaks corresponds exactly to energy levels. And this result we get using this blue crosses, which we get on a real quantum computer, Melbourne. And using this real quantum computer, Fourier transformation give also peaks. Not so good as we can expect, but nevertheless, using such bad result for time dependence, nevertheless, Fourier transformation gives peaks at the point which corresponds to energy levels. It was a surprise for us, but nevertheless, not so bad result for energy spectrum can be obtained in this case too. I omit the details of energy levels, say only that this peaks corresponds very nice to theoretical result. Nevertheless, results for time dependence is not so good. Fourier transformation gives good peaks for energy levels. Okay, but now we have the following problem. Not for all Hamiltonians we can find operator which anticommute with them. What we can do in this case? When we have Hamiltonian spectrum which is not symmetric with respect to inversion, we can I can state that in this case it is impossible to find operator which anticommutes with Hamiltonian. So now I would like to present you some generalization of idea which I presented you before. How to generalize method which use anticommuting operator for arbitrary Hamiltonian. Idea is to use probe spins or spin or ancilla qubit. So let us we have eigenvalue problem written here. Okay, written here, and we construct now some total Hamiltonian, which is constructed using additional probe spin sigma 0 z, and we multiply initial Hamiltonian with this probe spin. And then when we consider energy spectrum of this total Hamiltonian, you can easily find that zero component, x component of Pauli matrix anticommutes this total Hamiltonian. So idea is the following. Instead of studying energy spectrum of Hamiltonian H, we consider energy spectrum of total Hamiltonian, for which we can easily find anticommuting operator, because we construct, in fact, we construct such Hamiltonian for which we can find energy spectrum. You can easily verify that energy spectrum of this Hamiltonian is symmetric with respect to inversion because of this operator sigma 0 z. So then all results which we considered before, method which we considered before, can be used also for total Hamiltonian. And in this case, we also have supersymmetric algebra corresponding to symmetric properties of energy spectrum of total Hamiltonian. Let me omit explanation of this algebra. And a protocol for study evolution of Miller value of probe spin in general written here. Here once more we create initial state of our system, which is superposition of all possible states of spins, then operator of evolution, which corresponds to evolution of total Hamiltonian, and then we measure spin 0. Okay. So, and now I would like to present you spin sigma. How many time I have? Not so much.
5 minutes.
How many?
5 minutes plus 10 minutes questions.
Okay, thank you very much. So, of course, in order to verify this generalized method for calculation energy spectrum of quantum computer, I consider once more spinning magnetic field. I especially shifted energy spectrum to positive value. Let me omit details. And so here you can find energy spectrum of total Hamiltonian and two peaks which corresponds to positive energy spectrum corresponds just exactly to energy levels. Taking into account this shifting, you can easily find energy spectrum of two spins, and you can find it exactly reproduce theoretical result. Very simple system, and this generalized method work here very good. Okay, and more complicated system for which you cannot find operator which anticommutes with this Hamiltonian. Here, this Hamiltonian, it is 3 spins, it is chain, but chain in magnetic field. And here I especially consider magnetic field, which is exactly equal to coupling constant. So in this Hamiltonian, it is impossible to find operator which anticommutes with them. But when we construct total Hamiltonian, you can easily find that sigma 0 x anticommutes with total Hamiltonian. You can easily find method. You can easily use method proposed. So here is result for Fourier transformation using real quantum computer. Also very good result for energy levels we can get from these peaks. Here I would like to present very simple system, but the system where 2 terms does not commute. Also result is in good relation with theoretical result. Here is theoretical result for evolution. Crosses, it is real quantum computer result from real quantum computer. And here is energy spectrum which we get. So in the details you can find result from in this paper. So details is here. And very shortly, spin 1 tunneling. It's very nice and very interesting physical phenomenon, which is observed experimentally. And of course, because it's very simple system, it was idea to observe this phenomena using quantum computer. And using the method which we proposed, the method for calculation energy levels, we just calculate energy level for spin 1 system, which corresponds to a problem of tunneling of spin. So this is Hamiltonian, which describe spin 1 tunneling, single spin tunneling. It is spin 1. And spin 1, it is more complicated problem to simulate spin 1 on quantum computer, but spin 1 can be represented as 2 spin 1/2, and 2 spin 1/2 without single state. When we consider 2 spins and we omit a single state, then 3-dimensional subspace of this system absolutely corresponds to spin 1 system. Okay, so we can easily calculate theoretically result for energy spectrum, and also we can calculate using quantum computer. Here is this Hamiltonian rewritten using representation of spin 1 as sum of 2 spins. Interesting that this Hamiltonian it is anisotropic Heisenberg Hamiltonian. Here is operator of evolution. In order to calculate energy spectrum, we must have operator on evolution. Then we calculate mean value of sigma x of this total Hamiltonian. And then we consider Fourier transformation. This is theoretical result. We have a peaks at points which corresponds to energy level. And what we get using quantum computer. Here is protocol for calculation of mean value. Here we have 3 spins interaction, because we have 1 spin corresponding to probe spin or ancilla qubit, and we have 2 spins. So in fact, general total Hamiltonian contains 3 spins interaction. More complicated, but it can be done. You can construct such a protocol, and what is the result? The result is very good. We have energy spectrum, energy levels, 0 energy levels, and these 2 energy levels corresponding to degeneration of energy levels related with tunneling. So when constant of tunneling is larger, we have distance between these two levels also is larger, and so on. Its result is in very good in comparison with theoretical result. So we have good fitting of result which we get from quantum computer and result which we can calculate theoretically. This phenomena is interesting because it is not abstract model. It is a model which corresponds to experimental observation of spin one tunneling. And finally, we calculate also explicitly Z component of spin one. Z component of spin one show you exactly tunneling which we can observe here in this phenomena. These points corresponds to spin one. We have spin one with directed along positive direction of z-axis. Z as a result of tunneling, we have evolution, and here we have spin one directed along negative z-axis minus, and so on. So this absolutely corresponds to tunneling of spin one. Theoretical result, it is continuous line, which corresponds to dependence of this mean value on time, and result which we get on quantum computer. So details of this calculation and representation of spin one using two spins, one half, you can find here. All details is here. So thank you very much. And here in conclusion, you can I omit explanation of this conclusion. You can read here this conclusion. I only say that finally that method for detection of energy levels is stable with respect to errors which we have on quantum computers. So now we have very noisy quantum computers, but nevertheless this method show very good result. The method is stable with respect to errors on quantum computers. Thank you very much.
Thank you, Volodymyr, for this wonderful talk. There are various questions. Let me start with Shashi Kumar, who asked around equation 18. How can one find such an operator A which anti-commutes and also follows the constraints A psi mentioned? Does it exist for every Hamiltonian? And if not,
18,
what do we do in that
18,
case?
18.
Yeah, it was around this
Here?
slide.
This one?
I expect so, yes.
Yes, what is question? Question, why this operator sigma x anti-commutes with sigma z?
Yeah, how can we find such an operator A that anti-commutes and also follows the constraints A psi mentioned? Does it exist for every Hamiltonian?
No. Of course, no. Of course, such operator does not exist for arbitrary Hamiltonian. For some Hamiltonian, we can find such operator which anti-commutes with them. But not for arbitrary Hamiltonian, we can find operator which anti-commutes with such Hamiltonian. Just therefore, we propose a method which generalize this result. We propose a method which we call as a probe spin method. Using probe spin method, we generalize this Hamiltonian to total Hamiltonian for which we can always find operator which anti-commutes with them. So when we consider initial Hamiltonian, not always you can find Hamiltonian which anti-commute. In this case, it is simple to find such Hamiltonian. But when we consider, for instance, here, look here, in this case, it is impossible to find operator which anti-commutes with this Hamiltonian. But when we construct total Hamiltonians in such a way, you can easily find that this total Hamiltonian anticommutes with sigma 0x. Suppose a method which we proposed before can be applied to this total Hamiltonian. So in the answer is the following: when you cannot find operator which anticommutes with initial Hamiltonian, you can use in this case prop spin method. You construct more general Hamiltonian for which you can find for which such operator which anticommutes exist, and in this case it's sigma 0x.
Great. Lena asks, what is the advantage of using the Ising model?
Oh, of course, the Ising model is a very simple model because all terms anticommutes. Look here, for instance, let me show you. Advantage is, oh, it's here, okay. Advantage of this Hamiltonian is because all terms here anticommutes. First term anticommutes with second term and so on. Therefore, evolution operator, it is product of evolution operator for first term related with third term, related with second term, and so on. Therefore, in this case, we can very easy construct evolution operator. In general case, when here we will have, for instance, term which does not commute, it is more complicated problem to create on quantum computer evolution operator. In more general case, for instance, for Heisenberg model, it is necessary to use trautorization. So it is also possible, but for Heisenberg model, it will be necessary to use more gates. It is more errors, so on. So advantage of Ising model for calculation is in commuting all terms in this Hamiltonian.
Great. We have a few more questions, but little time. Johannes asks, could derivations from theory in such systems be a measure, benchmark of quantum noisiness of the QPU used? Have you tried other quantum computers and to compare?
Yes, because it's very interesting question concerning using different computers, because now computers is more good that computers which we used some time before. So it is good idea to use new computers which we have now to find the similar result and to compare this result. It was a good idea.